Hey everyone, welcome back. Today, honestly, it's gonna be a new type of video because there's basically no research done. Um, so we're just mostly gonna do live. I did like a few things, honestly. Um, so I'll just show that to you, and then maybe I'll be actually just watching a Khan Academy video. I'm just gonna record that and put it up. Just because I kind of want to keep the ball rolling. And also this Khan Academy thing, it's kind of interesting because it's like it was it's nice watching it now after doing all the stuff with GS ortho normalization because I'm like just kind of falling into the deep end and using my base level math intuition to understand that and then come back to this. It's like some validation there. Um, like very specifically, like if you look at the whatchamacallit, the units for the linear algebra skill, Unit 3's alternate coordinate systems, bases, orthogonal complements, etc., etc. So that made sense to me. But anyways, so today the exercise was number 6, right? We finished Gram-Schmidt orthonormalization. I mean, I could go back, make it an easy day, and just gotta adjust my seating posture, guys. Um, I could go back and redo this, like the Graham Schmidt or all the previous stuff, do like a mega video where I'm just doing everything NumPy only, which is an eventual thing I do kind of want to do, because learning NumPy is important. Also, I think I'm going to do it with some sort of visualization baked in, so I could use it to teach myself like some visualization libraries. And not like that I don't know NumPy or visualization libraries, it's just that, you know, I just kind of always found some code somewhere that kind of got to what I wanted. And with the rise of like Copilot and stuff, that process has become even easier. And so I feel like the deep internals of how they work is not something I've really deeply done. So I'd like to do that, but regardless, for now, I want to push through this entire thing. I kind of want to do this and the other data science math topics, your calculus and your statistics, and then wind around and be like, okay, we're going to do all this again in the actual libraries that are used like on a day-to-day basis in industry, right? Um, just to have another pass by at the info and the understanding and all of that jazz. Um, and then like maybe start doing things like XGB from scratch or neural nets from scratch, stuff like that. That's like kind of the vision I had. But anyways, eigenvalues and eigenvectors. We have to use the linalg module or linear algebra module of NumPy's to compute eigenpairs of a symmetric matrix. Verify AV equals lambda V for each returned pair. Optional advanced. Implement the power iteration method to approximate the dominant eigenvalue or vector. Now, library usage and convergence loops are what it's testing me on, apparently, but we're gonna not do library usage because using a library is really not that difficult if you understand the thing, which is why I'm like less concerned about those second passes and stuff like that. I really wanted to do basically as much as humanly possible in just pure Python before it like literally the cracks start to show. Then I'll start doing them like that with these more advanced libraries, and then maybe come back again and uh, do everything in those advanced libraries and not just like the end level stuff, which hopefully I'm gonna try at least give it a realistic shot to do it without these libraries and such. Anyways, this all was like honestly, I complete honesty, I've heard the word eigenvalues, eigenpairs, eigenvectors, all of that jazz so many times. I never actually knew what it was, so I just did what I normally do. I just popped it into ChatGPT I used it for mini high. And I guess I could have worded my prompt better because I just copy pasted the thing and I said, explain how to do this, don't give me any code. And just told me, make sure a matrix is symmetrical where A is equal to AT. I'm saying it says real and symmetrical. I'm assuming it means real as in it's just real numbers, which is easy. I believe all numbers are real numbers except for complex numbers and imaginary numbers, obviously. Um, I believe complex numbers are real numbers because they have a real component. But anyways, I'm not gonna get into that. Um, Symmetry guarantees all eigenvalues are real and eigenvectors can be chosen orthogonal. So I guess this is where what we did with Gram-Schmidt orthonorm will come in handy. And there's some process of orthogonality. Call the eigen decomposition routine, use this function. You get a vector and a matrix whose columns are the corresponding eigenvectors. Sorry, you get a vector of eigenvalues and corresponding eigenvectors. Each lambda I is a scalar that interpret the output. Each scalar, each eigenvalue is scalar such that exists a non-zero vector v with AV equals lambda v. AVI. A being, oh, the original symmetric matrix. There you go. For symmetric A, the eigenvectors vi are orthogonal. So V transpose V equals the identity matrix. Okay. Have to verify it. Okay, so I'll be honest, I don't think I read the rest because I came straight to this and I was just really unhappy with point number 2 over here. So I just kind of highlighted this and asked it to go into more detail. Uh, and then it started going on into this why symmetry makes life easier. Real symmetric matrix A always has real eigenvalues lambda. Its eigenvectors can be chosen orthonormal. Gives you when you back transform or check residuals, errors don't blow up. Okay, so I'm getting some of this right. So I understand the orthogonality giving you numerical stability, at least to some extent, I guess, because like some combos will end up being zero in your process of matrix or other multiplications. Um, Quadratic form interpretation. XTAX means how A reshapes the length of X. Reduction to a simpler form. See, yeah, I'm just like, my issue was that I was like reading through this and I'm just like, oh, I don't know what's going on here, right? It just seemed too intense. So I just came to linear algebra in Khan Academy. I started, and I'm like, okay, I feel like ground is trying to give beneath me. So I kind of wanted to speed run videos to try and like get more of an intuitive sense before I go back. I just started from unit one, though unit three is where the good stuff is. Um, I feel like as long as I don't spend too much time doing like um the what's the word I'm looking for? Like the exercises and stuff, I can blast through the understanding, especially because I think these actually I might just do them just because it's fun. We'll do them live, whatever. I think we could blast through this fairly quickly if I really tried. It'll be, let's see, unit one. Let's just look at it. I already watched 2 videos. Okay, there's actually a lot of videos here. Why are there so many videos and such few? Oh, here's the practice. I don't understand. Why is there no? So like here, there's like unit vectors, add vectors, blah blah blah. Everything else is just videos. What happened? Khan Academy is usually pretty good about like a bunch of exercises. Honestly, I might just do a bunch of exercises. See all 12 from my courses. Hmm. Yeah, okay. I guess this is just how it is. We'll blast through this. It's fairly simple. I think this video is, yeah, it's just literally stating that vectors have a magnitude and a direction. That's basically all this video is. Um, this video is just what are real coordinate spaces. So when vector the R with the number, uh, maybe you've seen that notation in some of the ChatGPT stuff from previous videos. Maybe let's see if I can find. Yeah, I'll be honest. I tried pumping it in ChatGPT, and I'm like, no, this none of this seems right. Rewrite some of X. Oh, okay. It did get some of X. Everything else seemed like wrong to me because I'm just like, no, this seems. Oh, Jesus. Okay. Anyways, whatever. We'll go into ChatGPT's proving my thing. But point is, I know I didn't really look at this. I just was like super tired because I did this right after that video in case anyone saw that. And then I went and checked, and it was just like I just couldn't comprehend. It didn't seem right. I just kind of went to bed, and then the next day when I checked it, it just came to me within like 10 minutes of sitting down and just looking at it carefully again with, rested eyes. Um, those with the asserts I'd gotten. Anyways, I can't find it, but it's like, yeah,
Or something. It's not hard to visualize things in 3 dimensions. But what's neat is that
just this symbol over here, R, right? That weird R to two-dimensional real coordinate space. That's like, I guess, the formal way to say it. I just presumed all real numbers like has a two for a vector, which is essentially what it is. It's all two tuples or all three tuples, I guess, formally um, uh, stated. But I mean, you could just say it like all pairs of real numbers, like all of them, all three couplings of real numbers that exist in all the world with replacement and all that jazz. Right? So essentially, the all of a certain coordinate space. Right. We talked about that. We move on to the next video. This is the video I was on. We're just gonna speed
two
watch it
two-dimensional
together.
vectors right over here, vector A and vector B. And what I want to think about is how can we define, or what would be a reasonable way to define the sum of vector A?
Preemptively apologize. I always listen to these things at 2x speed because it's like, especially with Khan Academy, like I can it's easier for me to focus, and it's like usually like revision, right?
plus vector b. Well, one thing that might jump at your mind is, look, well, each of these are two-dimensional. They both have two components. Why don't we just add the corresponding components? So for the sum, why don't we make the first component of the sum just the sum of the first two components of these two vectors? So why don't we just make it 6 plus -4? Well, 6 plus -4 is equal to 2. And why don't we just make the second component the sum of the two second components? So -2 plus 4 is also equal to 2. So we start with two two-dimensional vectors. You add them together, you get another two two-dimensional vectors. If you think about it in terms of real coordinate spaces, both of these are members of R2. I'll write this down here just so we get used to the notation. So vector A, and vector B are both members of R2, which is just another way of saying that these are both two tuples. They're both two-dimensional vectors right over here. Now, this might make sense just looking at how we represented it, but how does this actually make visual or conceptual sense? And to do that, let's actually plot these vectors. Let's try to represent these vectors in some way. Let's try to visualize them. So vector A, we could visualize. This tells us how far this vector moves in each of these directions, horizontal direction and vertical direction. So if we put the, I guess you could say the tail of the vector at the origin. Remember, we don't have to put the tail at the origin, but that might make it a little bit easier for us to draw it. We'll go 6 in the horizontal direction, 1, 2, 3, 4, 5, 6, and then -2 in the vertical, so -2. Yeah, just to emphasize, I could have drawn vector A like that, the direction, the magnitude, or I could have put it over here. These are all.
Yeah, this is I think an important thing in vector spaces, right? And this is another thing that kind of tied into why Gram-Schmidt orthonormalization is important, right? And I think that intuition that I developed there, where essentially you don't have vectors in this other space, right? Sorry, you don't have coordinates. You can't have coordinates in multidimensional space, at least not the way we understand it, which is already very abstract, right? We just like pick a point and we illustrate it, but it's actually an extremely abstract concept, right? And we illustrate 3 dimensions because we're able to perceive 3 dimensions with our eyes, but we can't really understand that in higher dimensions. So you need to form a basis on which you can do everything else in that higher dimensional space.
All equivalent vectors. These are all equal to vector A. All I really care about is the magnitude and the direction. So with that in mind, let's also draw vector B. Vector B in the horizontal direction goes -4, 1, 2, 3, 4, and in the vertical direction goes 4, 1, 2, 3, 4. So its tail, if we start at the origin, if its tail is at the origin, its head would be at 4, it would be at -4, 4. So let me draw that, just like that. So that right over here is vector B. And once again, vector B, we could draw it like that, or we could draw it. So let me copy, let me paste, and its sum is 2, 2. So 2, 2. So it would look something, it would look like this. So how does this make sense? That the sum, that this purple vector plus this green vector is some.
Saul's gonna do his regular thing where like, oh, you can just look at it. It kind of makes sense. And then it's like also it's just you add the X component of this one and the Y component of this one, and it just adds up. And you know what? It kind of makes sense because if you just look at it, like if you were to try and add up whatever that means, these two vectors, it does kind of look like it would go in this direction because both of these are kind of going in that direction. So it's like stilted in that way instead of like just being exactly in place. If you watch enough Khan Academy, you know what I mean.
Now going to be equal to this blue vector. I encourage you to pause the video and think about if that even makes sense. Well, one way to think about it is this
I preempted him saying that because I knew he was gonna do it.
first purple vector, it shifts us this much. It takes us from this point to that point. And so if we were to add it, let's start at this point and put the green vector's tail right there and see where it ends up putting us. So the green vector, we already have a version. So once again, we start at the origin, the vector A takes us there. Now let's start over there with the green vector and see where green vector takes us. And this makes sense. Vector A plus vector B. Put the tail of vector B at the head of vector A. So if you were to start at the origin, vector A takes you there. Then if you add on what vector B takes you, it takes you right over there. So relative to the origin, how much did you
Never mind, I'm an idiot.
which did you, I guess you could say, shift? And once again, vectors don't only apply to things like displacement. It can apply to velocity, it can apply to actual acceleration, it can apply to a whole series of things. But when you visualize it this way, you see that it does make complete sense. This blue vector, the sum of the two, is what results where you start with vector A, at that point right over there, vector A takes you there. Then you take vector B's tail, start over there, and it takes you to the tip of the sum. Now, one question you might be having is, well, vector A plus vector B is this, but what is vector B? What is vector B plus vector A? Plus vector A. Does this still work? Well, based on the definition we had, where you add the corresponding components, you're still going to get the same sum vector, so it should come out the same. So this will just be -4 plus 6 is 2. 4 plus -2 is 2. You would go there and you would start vector A's tail. I have gone 2 in the horizontal direction.
And the illustrations are good too. That's good to get that cemented geometrically. It makes complete sense. Actually, I'm gonna open up the next video tab because I'm a hoarder when it comes to tab groups, as you guys can see. I should close this actually. Oh,
A, and let's say that it is equal to 2 and 1 by A, which is the same thing, and reasonable thing by each vector to this vector. Well, 3, 4, 5, 6, and 3 the vertical. 1, 2, 3. So it gets us right over there. So it would look like this. So what just happened to this vector? Well, notice, one way to think about it is what's changed and what has not changed about this vector. Well, what's not changed is still pointing in the same direction. So this right over here has the same direction. Multiplying by the scalar, at least the way we defined it, did not change the direction that my vector is going in. Or at least in this case it didn't. But it did change its magnitude. Its magnitude is now 3 times longer, which makes sense because we multiplied it by from the scale. But let's do something. So let's exponents by negative times a. So now what happened? -1 by negative 5 to the left of 0. See, this would be the origin. It looks this. Let me draw this like this. So because of the negative, it has twice the magnitude in the other direction.
Yeah, that was just again, it's pretty straightforward.
In the last video, I was a little formal in defining what Rn is and what a vector is and what vector addition or scalar multiplication is. In this video, I want to kind of go back to basics and just give you a lot of examples and give you a more tangible sense for what vectors are and how we operate with them. So let me define a couple of vectors here. So and I'm going to do most of my vectors. I'm going to do ordered, looks like a comma, x1, x2, right? This could be called the second number axis, where each of the numbers, so each of them, x1 is a member of the reals, x1, and x2.
That's the weird E-shaped thing. It is a member, if that makes sense. I always thought it was subset of or something.
The reals, and just to give you a sense of what that means, that this right here is my coordinate axes, and I want to plot all my x1s, x2s, right? This could be, you could view this as the first coordinate. We always imagine that as our x-axis, and then our second coordinate we plot it on the vertical axis that traditionally is our y-axis. We'll just call that the second number axis, whatever. You could visually represent all of R2 by literally every single point on this plane if we were to continue off in infinity in every direction. That's what R2 is. R1 would just be points just abstract. I would be, I'll make it nice, and my vector, I'll just have each of them to entity 2. So
I think he's just doing a bunch of
then -4, and
basic
vector like another representation of this, and then add it to the standard details of the vector b. They all like that. It's the standard. So your number, the right 3, 1, 2, 3, and then up 1. This will be another representation of my vector b. There's an infinite number of representations of them, but the convention is to often put them in what's called the standard position, and that's to start them off at 0, 0. So your initial points, let me write this down, standard position. Vector A in standard position, I would start at 0, 0 like that, and I would go back 1, and then up 2. So this is vector 3, right, and then up 1. Rotation of the standard position. When you draw a tail end of B, you draw vector A, then you go up 1. So vector B, I have B here add plus 8 equal to 2 to the equally, I don't know if I terms. 2, this being is directed, this is our 2. I'll multiply it a vector, same symbol, same our definition. 1% minus, this is, let me draw this, 2 opens. Okay, I actually didn't want to draw collinear vectors. So let me draw here and go straight up, and you'll see that it's really the difference between the endpoints. This vector, this is my vector, x, this is equal to, let me switch colors, I don't like this color. Sometimes -1 is y, this right here is minus vector y. So this x minus y is going to be equal to 3 and 6. So let's see what that looks like when we visually represent them. Our vector x was, and then vector y is -2. So -1, -2. It looks just like this. -1, -2. It looks just like this. And actually, I ended up inadvertently doing collinear vectors, but hey, this is interesting too. So this is vector y. So then what's their difference? It says 3, 6. So it's the vector 3, 6. So it's this vector.
It's collinear vector. I mean, I think intuitively it just essentially means that the vectors are parallel, I guess. It's just, well, I like QMath. I remember I pulled them up for the Gaussian elimination video, or maybe the determinant video. Yeah, parallel. Just parallel. I was gonna say like literally occupying the same vector space, but parallel makes more sense, right? Because it could be in fundamentally different vector spaces, but they're still collinear. And because they're collinear, you can't solve them.
Let me draw it someplace else. If I start here, I go 1, 2, 3, and then I go up 6. So then up 6. It's a vector that looks like this. That's the difference between the two vectors. So you say at first you say, this is x minus y. Like, hey, how is this the difference of these two? Well, if you overlay this, if you just shift this and over this, you can actually just start here and go straight up, and you'll see that it's really the difference between the endpoints. You're kind of connecting the endpoints. But I actually didn't want to draw collinear vectors. Let me do another example. Oh, that one's kind of interesting. You don't see that one in the book. Let me define vector x in this case to be 2, 3, and let me define y.
So watch this.
That's if we difference, right? Like that's intuitively x minus y difference with 4, and then minus, and then minus 8.
I think he's just
right here 4 times this, you're going to get 0, 0.
And now it's just
So
doing
that's my.
multiple
So we take
dimensions to showcase that it works. Up next exercise. Should we do the exercise? We could do the exercise. Why not? Sure, quick. Yeah. One, two, three. What? So 1, so it'll be 1, 2, 3, it'll be here. And then it's 2, so it'll be -6 here. Check. A starts at the origin, ends at point B. Assuming 2v starts at the origin, which option could be its endpoint? A component form of vector w is -3, 1. Find -3w, so that's -3. And vector v has a magnitude of 6 units and creates an angle of 300 degrees with the positive x-axis. Oh, Jesus. Scalar multiplication component form and magnitude of direction.
What I want to do is give ourselves some practice and hopefully some intuition on multiplying a scalar times a vector. Now, what am I talking about when I say multiplying a scalar times a vector? Is one coordinate. Draw this, its y right here. Now, of course, I can put its initial point. It has a mag. What is 3? Now, the convention are, this is what 3w3, and like this, right? But the direction didn't change. Arrow now is 3 times. So let's say I graph it out into the y. Well, let's plot a little bit off of my axis, like. So we had the negative here. It just flipped its direction. If you consider this is long, it's twice the magnitude of our original vector, and it's the vector in opposite direction. Let me write it down. Scale might flip it around because of the negative.
Okay. One form is easy. Who's this about magnitude and direction?
All right, so we're told that vector v is equal to x comma y. So they're not giving us the actual number for the x component and the y component. They're just saying the x component is going to be the variable x, and the y component is going to be the variable y, and the magnitude of vector v is going to be.
This one's easy. Well, 1/3 of v will still create the same angle. It's magnitude of 6 units. Just 6 divided by 3 is 2. Okay. Oh, it's all.
We've already seen that you can visually represent a vector as an arrow, where the length of the arrow is the magnitude of the vector, and the direction of the arrow is the direction of the vector. And if we want to represent this mathematically, we could just think about, well, starting from the tail of the vector, how far away is the head of the vector in the horizontal direction, and how far away is it in the vertical direction? So, for example, in the horizontal direction, you would have to go this distance, and then in the vertical direction, you would have to go this distance. Let me do that in a different color. You would have to go this distance right over here. And so let's just say that this distance is 2 and that this distance is 3. We could represent this vector, let's call this vector v. We could represent vector v as an ordered list or a 2-tuple of, so we could say we move 2 in the horizontal direction and 3 in the vertical direction. 3 in the vertical direction. So you could represent it like that. You could represent vector v like this, where it is 2, 3, 2, 3, like that. What I now want to introduce you to, and we can come up with other ways of representing this 2-tuple, is another notation. This really comes out of the idea of what it means to add and scale vectors. And to do that, we're going to define what we call unit vectors. So unit vectors. And if we're in 2 dimensions, we define a unit vector for each of the dimensions we're operating in. If we're in 3 dimensions, we define a unit vector for each of the 3 dimensions that we're operating in. And so let's do that. So let's define a unit vector I. And the way that we denote that it is a unit vector, is simply an arrow on top. We put this kind of hat on top. It doesn't go at all. And then we can define another horizontal direction is going to go as is the sum, that vector v, purely in the horizontal, our unit vector, you could view as 2i and times j. Add this yellow vector. If you add the tail of the yellow vector like this, I action, as we'll see, b times the unit vector I plus 4 times the unit vector in the horizontal direction. So given these 2 vector definitions, what would be the vector v plus b? So let's think what we're doing, plus -1, adding the corresponding components of the vector. And then plus 4, 3 plus 4 times 1, j. I, and we could literally write that just as I. Actually, let's do that. 4 sevenths. We could represent it like this. -1, negative. If we were to add corresponding terms looking at them as column vectors, that is, and so if you were to add v to b, you add the corresponding terms. So this should be equal to, if we were to add corresponding terms looking at them as column vectors, that is going to be equal to 2 plus negative 1, which is 1. 3 plus 4 is 7. So this is the exact same representation as this. This is using unit vector notation, and this is representing it as a column vector.
Wait, what? Wait, let me read this. Okay, so he started with a vector 2, 3. He defined the unit vectors I and j. That makes sense. V equals 2i plus 3j. That's okay. Where did B come from? Oh, it's just, I'm assuming it's just another vector for the sake of an example. Negative 1i plus 4j. This is a, what did he call it? A vector representation?
Add V to B, you add the corresponding term like this. Color 2 plus 3. This goes back to now. How do we do that? Well, you could imagine vector v right here is the sum of a vector that moves purely in the horizontal direction that has length 2 and a vector that moves purely in the vertical direction that has length 3. So we could say that vector v, we do that same blue color, vector v is equal to, so if we want a vector that has length 2 and moves purely in the horizontal direction, well, we could just scale up the unit vector I. We could just multiply 2 times I. So let's do that. Currently doing this yellow. 3 times j. 3 times j. Let me write it like this. Let me get the color. 3 times j. Once again, 3 times j is going to be this vector right over here. And if you add this yellow vector, right over here to the magenta vector, you're going to get, notice we're putting the tail of the magenta vector at the head of the yellow vector. And if you start at the tail of the yellow vector and you go all the way to the head of the magenta vector, you have now constructed vector b. So vector b, you can represent it as a column vector like this, 2, 3, you can represent it as 2, comma 3, or you can represent it as 2 times I with this little hat over it, plus 3 times j with this little hat over it. I is the unit vector in the horizontal direction, in the positive horizontal direction. If you want to go the other way, you multiply it by negative. And j is the unit vector in the vertical direction. As we'll see in future videos, once you go to 3 dimensions, you'll introduce a k. If you can represent it as the tail of the yellow vector right over here to the magenta vector, you're going to get, notice we're putting the tail of the magenta vector at the head of the yellow vector, and if you start at the tail of the yellow vector and you go all the way to the head of the magenta vector, you have now constructed vector b. So vector b, you can represent it as the tail of this 3, so plus j. Once again, magenta vector, your vector, you have 2 times I with this little hat over it, plus 3 times j with this little hat over it. I is the unit vector in the horizontal direction, in the positive horizontal direction. If you want to go the other way, you multiply it by negative, and j is the unit vector in the vertical direction. As we'll see in future videos, once you go to 3 dimensions, you'll introduce a k. But it's very natural to translate between these two things. Notice 2, 3, 2, 3. And so with that, let's actually do some vector operations using this notation. So let's say that I define another vector. Let's say it's vector b, and vector b is equal to.
The reason I'm like pausing and going back is like I just want to hear the formal name of it, like what these two representations are called. I think it's I actually don't know. One of these is I guess column vector representation is the one with the square with the brackets. I wonder what the I'm just like, what is this called?
Let's come up with some numbers here. Vector b is equal to negative 1 times I, times the unit vector I, plus 4 times the unit vector in the horizontal direction. I encourage you to pause the video and think about it. Well, once again, we just literally have to add corresponding components. 2, say, okay, well, 2 plus negative 1, 2 plus negative 1 in the horizontal direction, and we're going to multiply that times the unit vector I. And this, once again, just goes back to adding the corresponding components of the vector. And then we're going to have plus 4, or plus 3 plus 4, let me write it that way, plus 3 plus 4, 3 plus 4 times the unit vector j in the vertical direction. And so that's going to give us 2, I'll just solve this one color. 2 plus negative 1 is 1, I, and we could literally write that just as I. Actually, let's do that. Let's just write that as I. But we got that from 2 plus negative 1 is 1. 1 times the vector is just going to be that vector, plus 3 plus 4 is 7, 7j. This is exactly how we saw vector addition in the past, is that we could also represent vector b like this. We could represent it like this. Negative 1, 4, negative 1, 4. And so if you were to add v to b, you add the corresponding terms. So this should be equal to, if we were to add corresponding terms looking at them as column vectors, that is going to be as this. This is using unit vector notation, and this is representing it as 3 plus 4 is 7. So this is the exact same representation as this. This is using unit vector notation, and this is representing it as a column vector.
Ah, okay, so it's just called unit vector representation. I can't believe I wasted that much time on it. Oh well. Next exercise, why not? This video is going to be called Khan Academy and chill. I can feel it in my bones. No. Oh Jesus. Ugh. That is in the direction of V. The hell? Well, okay. How do you normalize a vector? You divide by its magnitude. How to get its magnitude? The L2 norm is the square rooted, right? Sum of squares square rooted, so 4 times 4, 16. 8 times 8, 64. 64 by 16, 80. Root 80 is fine. So just I need The one with both of them having negative signs. Yeah. I'm going to see the step-by-step solution. Make sure I'm right. Yeah, just the root squared the L2 norm. I keep calling it magnitude, but that's very specifically the L2 norm or Euclidean norm. We already did that. Find the unit vector in the direction of 3, 4. So 3 squared 9, 4 squared 16. 16 plus 6, 20 plus 3, 23. 23. 23 decompose. No. 23. Oh, yeah. Why does this keep happening? Oh, but why? Oh my god, Khan Academy. The hell? Oh, I see what the issue is. There you go. Jesus Christ, that was weird. Uh, dude. Let's see, it's probably decomposition. Wait, how 3 squared is 9. Oh, yeah, it is 25. I don't know what I'm thinking. Well, it's okay. 5. 5, whatever. Select the unit vector in the direction of this, I believe, right? 5 squared plus 5 squared is 25 plus 25 view 50. Yeah, it's actually this. 8 squared is 64 plus 4 is 68. Let's hope it doesn't decompose. Is there a square root button on my thing? No. Square 68. Negative 8. Square 68. Let's check. Yeah. Bonus question. Bastards. Select the unit vector in the direction of v negative 5, negative 4. 5 squared is 25. 4 squared 16. 25 plus 10, 35 plus 4, 39. Root of 39. Oh, it has to be. Is it though? 4 squared is 16. 5 squared is 25. 25 plus 10, 35. How's this 41? Isn't 5 squared? Five. How do you do squares here? Square. All right, 16. Oh, wait, I'm stupid. Why? I don't know how to do math. I'm doing my arithmetic wrong. It is 41. I'm stupid. Okay, so they're both negative signs. We're just looking for the ones with the F. There it is. There's another exercise. Adding vectors. Fun. Okay. Draw the resultant parallelogram. Skip. You know what? Screw this. It's not. Oh, what? R and theta, where R is the magnitude and theta is the angle. In 25 to 4. So it'll be what, 8 plus 5? 13. And 260, yeah? Oh, Jesus. Geometry, no! I should probably do a geometry thing as well. Hmm. We're gonna skip that.
Everything we've been doing in linear algebra so far, you might be thinking as it's kind of a more painful way of doing things you already knew how to do. You've already dealt with vectors, or I'm guessing that some of you all have already dealt with vectors
This is a 25-minute video.
in your calculus or to do. So on top, I'm going to define my vector v. I can do it. If I were to draw it in standard set S, and it's equal to all the vectors I can, all the possible vectors I can create. So let me define a set. Let me define a set S, and it's equal to all the vectors I can create. If I were to multiply v times some constant, so I multiply some constant, some scalar, times v times my vector v, and I'll just to make it a little bit formal, I say such that C is a member. I don't want to write. C is a member of the.
All right, it's like 2 a.m. I can't keep my eyes open. Thanks for watching, guys. Hopefully we won't just be doing another Khan Academy and Shield video tomorrow, and I can like actually talk. Thank you so much for watching, guys. Have a great one.